So far we have already covered the mole concept. We have already covered the solution chemistry, where we learned about the concentration, and now and also we did a little bit of the empirical analysis. Okay, so now we are doing the stoichiometry of chemical reaction. Stoichiometry of chemical reactions. Okay, all right, guys. So let's do this. So basically, uh, stoichiometry of chemical reactions, trust me, it is very, very easy with the concepts of the unitary method, actually. Okay, like so far we have been doing unitary method, and people do ask sometimes in maths, when they are being taught something, they think that like why that specific thing is being taught. Okay, so every concept that you are learning, okay, is being used, okay, somewhere in your life. Every concept that you're learning, trust me. Okay, even if if I'm talking about the stoichiometry, okay, even if you're not going to take chemistry in future, okay, still you'll be using it somewhere. Okay, see, the thing is, whatever we are learning with that, like we are broadening our spectrum of thought, actually. Okay, so we are able to think widely, right? So talking about the stoichiometry of chemical reactions, the very important thing and the very first thing that you are supposed to know is the stoichiometric ratio. So what is that? What is stoichiometric ratio? See, the thing is, when I consider a reaction, let's say H2 plus O2, and that is giving us H2O. Okay, so what do you write? 2H2 plus O2 giving you 2H2. Easy, right? Now, what is the coefficients you are seeing over here? So these are basically the coefficients. This is the coefficient. What is the coefficient over here?
1.
Yeah, so this is 2:1:2, right? This is 2:1:2, right? What is this? This is nothing but this is the stoichiometric ratio. What does this mean? That you, if you're trying to make water from hydrogen and oxygen, okay, one thing is sure, that like always 2 moles of hydrogen will be combining with 1 mole of oxygen to form 2 moles of water. Okay, whether you are forming it in a very, very high temperature pressure condition, low temperature pressure condition, on earth, inside the volcano, or be it like any part of the universe. Okay, so this particular stoichiometric ratio gonna be constant. Okay, so this stoichiometric ratio is the most important part of this particular topic, right? And what is this stoichiometric ratio about? It is basically, it is the ratio of number of moles. This is the ratio of number of moles which you determine from the coefficients in the balanced chemical equation. Okay, this is the balanced chemical equation. So from there, the ratio that you are getting is known as the stoichiometric ratio, which is the ratio of number of moles. Okay, it can be also known as the ratio of number of molecules, actually, ratio of number of molecules also. Okay, but it is not equal to the ratio of masses, okay, but it can also be equal to, it can also be equal to the ratio of volumes of gases, if the gas is inward, obviously. Volumes of gases, obviously, if gas is inward, right? So this is the thing. Yeah, so stoichiometric ratio, which you are determining from the balanced chemical equation, is giving you the ratio of number of moles, or it can be the ratio of number of molecules. It is not equal to the ratio of masses. It can be the ratio of volumes of the gases. Okay, you already know that 1 mole of any gas at STP, is 22.7 bm3. Okay, and this is the reason that we can actually consider. So you can see that like 1 mole is basically corresponding to a constant number. Okay, and that's why if it is the molar ratio, it can be the ratio of the volumes of the gases also. Okay, but at the same time, when I'm comparing with the masses, see why it is not equal to the masses. Like suppose if I'm considering the water, so 1 mole of hydrogen is 2 gram. Okay, and 1 mole of so 2 moles of hydrogen is equals to 2 moles of hydrogen will be equals to 4 gram. Agree?
4 gram. Yes, sir.
4 gram. Now 1 mole of oxygen we have used. This is 2:1, right? So 1 mole of oxygen is 32 gram. Okay, so the ratio is 1:8, right? Isn't it? So the ratio is not corresponding to what we are getting for the ratio of masses, right? So it is not equal to the ratio of masses. Is that clear, guys? All of you? So remember, by default, you should use just one of them. By default, just use one of them, and that is the ratio of number of moles. It is always true. Always true, right? The thing is, hardly we use the ratio of number of molecules. Not very much required. Okay, hardly we use the volume of gases. We use this thing only if the gases are involved. Okay, otherwise we don't use it. So this is something which is best to be used, right? Always use the ratio of number of moles to determine the stoichiometric ratio. Okay, or when you're working with a stoichiometric ratio, just use the ratio of number of moles. Is that clear, guys? All of you?
Yes, sir.
Cool. Let's go ahead. So suppose here I'm giving an example. For example, if I'm having KClO3, 2KCO3, giving you 2KCl plus 3O2. Now this is balanced chemical equation. All right. So the question comes that, let's say this is 24.5 gram. Okay. And how many grams of this will be produced, and how many dm cube of this will be produced? That is the question. Okay, how many dm cube or how many cm cube of this is produced? All right, so this is the question. Remember the very first step: convert the given data into number of moles. Convert given data into number of moles. Cool. So, so if I'm converting the given data into number of moles, so what data, first of all, I'm given? I'm given the mass of KClO3, right? Mass of KClO3, which is 24.5 gram. This is given. Now, we have to convert it into the number of moles, right? So, what do we want? We want number of moles of KClO3, question mark. What formula should be used?
Mass upon molar mass.
Exactly. So we know one thing, that the number of moles is equals to mass upon molar mass. So the first step should be determining the molar mass of KClO3. So what is potassium? Potassium is 39 plus 35.5, that is chlorine, and 3 times 16. Come on, guys. Please tell me what is the molar mass of KClO3 quickly.
122.5.
Shabash, 122.5. So we get the number of moles with 24.5 divided by 122.5. Come on, tell me the answer.
0.2. I already did this question.
0.1.
2.
The ratio will be 1.
All right. Don't go ahead. Okay, let me explain. The second step is compare the known and unknown with the stoichiometric ratio. Compare the known and unknown with stoichiometric ratio, right? With stoichiometric ratio. So what does that mean? So basically, the next step, comparing with the stoichiometric ratio. This means what? That we are given KClO3. I can compare it with KCl. Now the ratio is 2:2, right? This is 2. This is 2. So 2:2. So if this is 0.2, how much this should be?
0.2.
0.2.
Exactly. So we get number of moles of KCl equals to 0.2. And we want mass of KCl. For that, which formula to be used? Again, number of moles equals to mass over molar mass. So we need molar mass of KCl. Molar mass of KCl is 39 plus 35.5. What do we get?
74.5.
Shabash, 74.5. So we get mass of KCl over here with the formula. Mass will be equal to the number of moles into molar mass, 0.2 into 74.5. Please tell me the answer.
14.9.
14.9.
14.
14.9 grams. So this is the thing that we obtained. Now, same way we can actually work on the oxygen over here. The ratio is 2:3 from the equation. 2:3.
Yes.
Yeah. So 0.2. So what this should be? So this should be number of moles of oxygen should be 0.3, right?
Hmm.
Now, what do we want? We want volume. So how the number of moles related to the volume of the gas?
Mole with the 22.7 volume formula.
Correct. So number of moles is equals to volume over 22.7. So volume will be equal to number of moles into 22.7. That is 0.3 into 22.7. What is the answer that you are getting, guys?
4.54.
Huh? 4.54.
54.
When you multiply this by 1000, that will give you the answer in centimeter cube. 4540 centimeter cube. Yeah. So basically, here the third step is determine the number of moles of unknown, number of moles of unknown, and then finally the last step is determine the mass, volume, or concentration. Okay, as asked in the question, right? So whatever is being asked, that you need to do, right? So these are the steps with the working. I hope everything is clear to all of you.
Yes.
Sir, I have a doubt.
Go ahead.
Sir, we multiplied 0.3 into 22.7 to find out the volume, right?
Yes, obviously.
So that should be 6.81, right? 0.3 into 22.7.
Not my mistake.
Oh, sorry. Whoever said it, it's 6.81, 0.3 into 22.7.
6.81. Okay. So
That's 6.8.
this is 6.81, guys. So whoever told me that wrong answer, please check if you are wrong or if meat is wrong.
I said the answer. I did calculation error. My bad.
Please don't do that kind of errors. Even after knowing the concept, you lose marks, you lose your grade. Okay, so please make sure you are not doing any kind of silly mistake. Okay, so guys, I hope everything is clear. Should I go ahead
Yes,
with the
sir.
question?
Yes,
Yes,
sir.
sir.
So let's do your question. I already taught you people how to balance the chemical equations, I remember. Right?
Yes, sir.
Yes.
So 4H3 5O2 4NO6H2. Now you are given that this is of 5.1 gram. Okay. So you need to determine what cm cube of this will be used, what gram of this will be produced, no, what dm cube of that is being produced, and what gram of this will be produced. Okay, so three things, right, guys? Come on, do it. I give you 5 minutes. Yeah, what answer you got over here?
For H2O, I got 8.1 grams.
Same.
Same.
For NO, I got 6.81 dm cube.
Yeah,
Yeah.
same.
And then for oxygen, I got 8512.5 cm cube.
Yep. Same.
So let's
0.5,
get
sir.
this.
0.5. Decimal after 8512.
Okay,
And then it's
8.1.
And NH3 is 0.3 mole.
All of you got the same answer, is it?
Yes.
Yes.
All right, so this is 6.81. Let me just check. This is 0.3, so NO also should be 0.3. So 0.3 and multiplied by 22.7. And yeah, seems good. Hmm. Yeah. 0.0.45 times 18 is yeah, exactly 8.1. Correct. And this is yes, absolutely perfect. Shabash. All right. So the next one more question. Here you have Fe2O3 plus CO, 3CO, giving you 2Fe plus 3CO2. Okay. So what you're given is this is 4.8 gram reacting with certain DMQ of CO, producing certain gram of Fe and producing certain gram of CO2 also. Come on, do it.